Good afternoon, class. We've got ourselves an online lesson today, and I don't have my graphics tablet because it was locked in the school over the long weekend. So we'll have to do our best with PowerPoint. That's all right. So today we're going to be looking at the really interesting approach that Millikan and Fletcher did in the determination of the charge of an electron. This is well, we'll have a couple questions that'll be somewhat related to it, but nothing quite as involved as what they're doing. But I think this is really valuable to go over because this helps show a process and an interesting way for us to gather data. This kind of thing, like this is really where experimental physics is coming into its own. Right around this time is where experimental physics is really leapt forward leaps and bounds beyond what the people can see. And I think this is a really excellent example of methods of data collection, which isn't necessarily as straightforward, but when you see it, you're like, oh, and I think it's pretty wonderful. So let's get a start in and look at the Millikan oil drop experiment. So just start here. 1909. This is about the time that's happening. Robert Millikan, Harvey Fletcher. They conducted an experiment. They wanted to determine the charge of a singular electron. We were aware at that time that there were these subatomic particles called electrons, but its properties, its mass, and its charge were unknown to us. We just didn't know what it is. All we saw was that there was charges that traveled when you applied electric fields to it, and we were kind of like, that's about it. So what they ended up doing, they wanted to find more about the electron, is they made a chamber where they would spray some oil through a charged grate. They would spray some oil and it would friction charge on the nozzle, just like the same way that you would friction charge a balloon on your hair, right? Rub a balloon on your hair and there's some transfer electrons. So there's some friction charge between the oil as it's rubbing through the nozzle of the sprayer. You can do that just by slightly charging a metal sprayer, give it a little bit of a potential, and it should be fine. So that's kind of how they did it. And then they put a hole, and then they let that drop down, that oil mist that now has electrocharge, they let it drop down, and it would go through a hole in an upper plate that would allow oil drops to go into a chamber where they had a microscope, just like this. So you can see that there's the oil sprayer that made a mist, and then the oil drops would come down, and there'd be a little hole that a charged oil drop could come in, and the two plates there are charged plates. So you can apply electric fields, and you'd have a little knob or a little dial that could control how many volts, the volt difference across those two plates. And you'd use your microscope to keep an eye on the oil droplet. So now we know we could observe it, we have it charged, and we can observe it, and we can manipulate it by manipulating the voltage. We can manipulate that droplet by manipulating the voltage. Now imagine, for example, or sorry, before I move on, so for us to determine information about that, we need to know a bunch of information about this droplet, like how big is the droplet? And that's actually a big question. If you have a sprayer, how big is each droplet? Are they all going to be uniform size? Probably not. So we need a way to measure this droplet, and you can't get a ruler in there. It's not going to work. So, and like we have to use microscopes to see these droplets in the first place. So we need to determine an alternate way to find the size of the droplets, because if we can find out the mass of this droplet, then we can go from there. So they're all small, but they're not necessarily the same size, and so the mass of each droplet is an unknown. The density of the oil is easily measurable when you just have a bunch of the oil, right? You can just have a bunch of the oil, you can just measure the volume, measure the mass. Awesome. You can know the density of the oil, and so the droplets are spherical. Most fluids, when they are put like placed into airs or misted, become spherical, so that's nice. we can use the fact that we know the volume of a sphere is 4/3 pi r cubed. So awesome. If I'm thinking 4/3 pi r cubed for the volume, and I know the density, volume times density is mass. So the only thing missing is the r, is the radius. But we have no way to measure the radius of this droplet. This is where forces are going to help us. If this droplet is falling, and say we have not turned on our charged plates, this is its free body diagram. Gravity is pulling it down, and then there's some drag that's pulling it up, that's resisting the fall. Now, if we use our mass formula, m is 4 pi r cubed over 3, or 4 pi r cubed over 3 times the density, we actually have the drag force, which is determined through Stokes' friction formula. Stokes, what he did is he ended up determining the drag formula for anything moving through a fluid. When we're talking about fluids, we're talking about materials where things can move past each other. So any liquid or gas, liquids and gases are actually fluids in this case. So the force of the drag would be 6 pi nu, where this n, this Greek n, is the fluid viscosity of the air, so that's measurable, and r is the radius of the droplet, and v is the velocity of the droplet. So the net force on this droplet would be the gravity pulling down, subtracted by the drag going up. And if we substituted in, net force is mass times observed acceleration. Gravity is m times 9.8. That's our g, minus the drag formula. Substituting the 4/3 pi r cubed times rho, or times the density formula for mass, we can get that third line of math there. That's just a substitution. And then just do a little bit of algebra, wiggle, 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 right? Algebra around, and we have now found, like, aha, the radius can be found as the square root of 9 nu v over a minus g. Acceleration, now the only unknowns here are velocity and acceleration. For us to determine this, we just have to figure out, well, how fast is it falling and what is its rate of change of falling. And that's something you can observe. You'd set up perhaps you'd set up a grid system behind the droplet. And since you're observing, you'd be able to time as it falls past this grid system. So you'd be able to take some displacement and time measurements as it's falling. And so with those displacement and time measurements, you would end up plotting those. Velocity, for those of you who are comfortable with calculus, velocity is just a rate of change, or the acceleration is the rate of change of velocity. So you'd be able to actually change either your velocity or your acceleration to be a derivative or a rate of change factor of the other one, so you can have just a singular function, and you'd be able to plot your function of velocity to, or plot your velocity over your displacement first time to figure out your velocity and your acceleration at this time. And that will help you find the radius. And in finding the radius was the only thing we didn't know about our mass. So if you're like, scary math, don't worry, you don't have to do this math. Millikan already did it for us. But this is just showing that with a setup here, this is with the setup where you have just like a grid system behind, like a grid system behind the droplet, and you're observing it, you'd be able to time how far it fell. You'd be able to determine its acceleration, and by finding the acceleration, you have now found all of the terms needed to find for the radius. You now know how big that droplet is. So Millikan and, what was the other guy's name? Fletcher, there we go. I always forget. It's always Millikan's oil drop. I don't know why Fletcher doesn't get any credit. Oh well, history. It's the way it works. But Millikan and Fletcher, what they do is they spray let those oil droplets begin to fall, and they'd be measuring out, and they do this multiple times, so they'd be able to determine the mass of each droplet as they were observing it. Now that we know the mass of each droplet, it's time to turn on our voltage. Remember how we had these parallel plates? Well, with these parallel plates, then when you turn that field on, then it's going to be forcing the electric charge upward. Remember that while it looks like the uniform electric field is pointing downward, the electric field is the direction a positive charge goes. But these oil droplets have lots of extra electrons, which are negatively charged. So due to the negative charge, the electric force is going to be forcing them upward. And so with that, we get a new free body diagram where your electric force is pulling upward and your gravity is downward. Now, this free body diagram only exists if this is levitating, if there's no drag. If it was moving up or moving down, we would introduce that drag force up or down, depending upon where it's going. But because it's easiest to look at the math when it's levitating, right? You can tune your voltage, so it's like, oh, perfect. The force, the gravity pulling it down is exactly equal to the electric force pulling up. That's the easiest one for us to look at. Let's take a look. The net force then would be the gravity pulling down, the electric field pulling up, and then plug in, like, do these substitutions: mass, acceleration, mass times the acceleration caused by gravity, and the electric field times the charge is always going to be equal to the force, so I substitute in there. Now, how do I produce an electric field in parallel plates? That's the change in voltage, or the potential difference across the plates over that separation of plates. That's what D is. So a little bit of rearranging there, and we were like, aha, we can now find the charge because we have found M. We did that earlier, letting the droplet fall up and down. We're letting that droplet fall thing to help us find the mass. Separation of plates, that's just one of the constants in your situation. G minus A, that's the gravitational field. A is the acceleration, assumedly in the case of levitation, the acceleration 0, over the potential difference, and that's the thing that you're tuning. The potential difference is your independent variable, and the charge there is the dependent variable that you'd be looking for. And this way, hey, we're able to find out the charge on these oil droplets. Isn't that really interesting, right? We could find the charge on these oil droplets. Now, that's awesome. Millikan and Fletcher are now finding charges on oil droplets that are friction charged. Little problem. Do we know how many electrons are going on each oil droplet? Hopefully you are shaking your head, probably silently, because I'm not there for you to talk to. Yeah, that's the reason, probably. So no, you have no chance of figuring out exactly how many electrons got on there. So how can we say that Millikan in this oil drop experiment actually found the charge on an individual electron? Well, this is the extra part that got really interesting, because Millikan and Fletcher also knew that they didn't know how many electrons going on, but they did this experiment many times. And in doing it many times, they're able to find a variety of different charges. And when they did that, they were able to determine that there was always a certain difference in the charges, some integer value of some integer multiple of a particular value. So what they said is that, like, they were like, okay, we find that we're getting this variety of charges, but but the differences in charges can always be attributed to a set number or some integer number of that set number. They hypothesized then that set number that they got was the charge of the electron. And so what they're doing is they're using by inference. The concept here would be like saying, if you're doing an experiment, maybe a similar type of experiment, and you found that one person had one person had 10 objects, and the next person running through had 7 objects, and another person running through had 4 objects, and a person running through had 15 objects, and you're like, what is the smallest difference that I can get by all of these? And so you check the difference and you see if there's any common sets of multiples that would be able to fill the gaps in between all of those. That's what they did, and except they didn't know the numbers. So they just had to take lots of data and they had to determine what is the smallest difference that I can get based off of these values. And they ended up finding the charge of an electron. It was really cool, a really interesting way of actually determining through inference. They did not measure the charge of an electron. They measured the charge on an oil droplet and did a whole ton of different oil droplets to be able to infer the charge of an electron. And this kind of approach, where you might say it's like kind of trying to approach the problem sideways, is fundamental in a lot of our research that we have nowadays, because especially as you get to very small quantities, and this is where the concept you might have heard of the Heisenberg uncertainty effect, is the act of measurement changes the thing that you're trying to measure. So you that is like so fundamentally challenging. How do I measure something if by trying to measure it I change whatever it is? And so what we often do is we measure the effect that that thing had on the world around it. And that's so we measure by inference more often than anything else when we're talking about really, really small and, in fact, very, very large um, things, things that are outside the classical scale. Because trying to measure directly is impossible, because we fundamentally will just manipulate and change the results. It's very, I think this is a really excellent example of a experiment that showed the power of measuring by inference. All right, I hope you found that to be a really interesting experiment. I found this experiment to be truly fantastic. In Fletcher and Millikan's, to their credit, they were correct. Their results were verified by determining the charge to mass ratio of electrons, and that one is actually really, really fun. That's a really fun experiment. I had to do that in my second year labs. Had to sit in a dark room all by myself to do it, but it was really cool. So the charge to mass ratio helped verify it, and there was another experiment that helped verify it, but I forgot which one. That's okay. So yeah, on the worksheet there are some problems that are looking at the Millikan oil drop experiment style of problems. They are not going to be like the determine the drag coefficient, or that's not what it's about. It's mostly utilizing the the net force equation that you see here, is where gravity is pulling down some charged object and we're using some electric force to levitate it, um, like we see in this. So take a look at the problems on the worksheet. You'll notice that they are going to be focused on this. Think of a free body diagram. You might have to use the separation of plates to determine the electric field times charge is force, stuff like that. Other than that, that should be it for today. Practice up. See you tomorrow.